Researchers were interested in comparing two methods for estimating tire wear. The first method used the amount of weight lost by a tire. The second method used the amount of wear in the grooves of the tire. A random sample of 16 tires was obtained. Both methods were used to estimate the total distance traveled by each tire. The table below provides the two estimates in thousands of miles for each tire. Part A, we wish to construct and interpret a 95% confidence interval for the mean difference mu in the estimates from these two methods in the population of tires. All right, so as you can see, I already have my state. We want to estimate the true mean difference mu in the estimates from these two methods in the population of tires at the 95% confidence level. Okay. So the first thing we need to do is we need to do our plan. And the first thing I've noticed is that we have 16 data entry points, right? So remember, we don't have that 30, that magic number 30 to use the central limit theorem. So we're going to have to use our T procedures, and in order to get that normal condition for the T procedure, our sample size needs to be at least 15, which it is. Okay, and we can use this T procedure except in the presence of outliers or strong skewness. So we have to figure out if this data has outliers or strong skewness. So our plan is going to be, since n is equal to 16 and that's less than 30, and we do not know the population standard deviation, we need to use a one sample T interval for the population mean if the conditions are met. So the first condition, right, is random, but we were told in the problem that the data was collected randomly. So the data came from a random sample. So we're good there. Now we have to check this normal condition, right? Normal condition. Okay, so we have normality when there are no outliers or strong skewness. So we have to go to our calculator. So I already put in the values for the weight, right? And I put in the values for the groove, okay? So now I made a column for the difference. How we can calculate the difference is you click here, right? And you're going to do column A minus column B, okay? Then you're going to hit enter. And this is the weight column minus the groove column for each of these data points. All right? So once we have that difference, this is the one variable statistic that we're looking for in order to do our outlier test and to check for a strong skewness or not. All right? So once we have that, we can go to menu. We can go to statistic, stat calculations, one variable statistic. Okay. And we're getting our data from the C column. That's our differences, right? And we want our results in the D column. All right, so there we go. Here are our one variable statistics for that C column. So our X bar is 4.556. Our sample standard deviation is 3.225. Our minimum is negative 0.5. Quartile 1 is 2. Median is 4.35. Quartile 3 is 7.15. The max is 10.2. And that's all we need to determine if the data is strongly skewed or has outliers. So now let's go back to our problem. Okay, so here we go. X bar, right? X bar was equal to 4.556. Our standard deviation is equal to 3.23. Quartile 1 was equal to 2. The median was equal to 4.35. Quartile 3 is equal to 7.15. The min is equal to negative 0.5. And the max is equal to 10.2. So now let's go ahead and do our outlier test. So outlier. So the first one, outlier test. Okay, so it's quartile 1 minus 1.5 times IQR, which is quartile 1 is 2 minus 1.5 times, so IQR is 7.15 minus 2, which this gives us negative 5, 0.725, which is less than the min. So there are no outliers left of the distribution. Now let's try right of the distribution. So quartile 3 plus 1.5 times IQR, and that's going to be 7.5 or 1.5 plus 1.5 times 7.15 minus 2. This is going to equal 14.875, which is bigger than the max. So this tells me that there are no outliers, right? No outliers left of the distribution and no outliers right of the distribution. So again, x bar was equal to 4.556. The median was equal to 4.35. And the standard deviation was equal to 3.23. So we can see that x bar is bigger than the median. So this implies that the distribution is right skewed, but as long as it's not strongly right skewed, then we have that normal condition satisfied. So the way we're going to determine that is if the median is within half a standard deviation of x bar. So we'll have x bar minus 0.5, the standard deviation of x bar plus 0.5, the standard deviation of x. This is equal to 4.556 minus 0.5 times 3.23, and then 4.556 plus 0.5 times 3.23. And this interval is going to be 2.941 and 6.171. All right, so we can clearly see that the median is within half a standard deviation of x bar. So this tells us that the distribution is only slightly right skewed. So m is within half a standard deviation of x bar. So the distribution is only slightly right skewed. Slightly. All right, so that means our normal condition is met. All right, so now let's check our independent condition or our 10% condition, right? All right. So little n has to be less than or equal to a tenth of big N, where big N is all tires, right? So clearly we had 16 is going to be less than a tenth of all tires, right? Or we can rewrite this as 160 is less than or equal to all tires. So all conditions are met, right? Okay, so since all the conditions are met, we can now do our do part. So n is equal to 16, which implies that the degree of freedom is equal to n minus 1, which is 16 minus 1, which is 15. So since this is a confidence interval, we have to do 1 minus 0.95 over 2, which is 0.025. So this means our critical value for the t is, so let's go to the table. So we have 0.025 and 15. Well, let me go back, right? I don't need all that. 15, right? So that is right here at 2.131. So our critical value is 2.131. So 2.131. So our 95% confidence interval, scoot down, is going to be x bar plus or minus the critical value times the standard deviation of x over the square root of n, which this is equal to 4.556 plus or minus 2.131 times 3.23 all over the square root of 16. And then this gives us 4.556 plus or minus 1.719. And then this gives us the interval. So this gives us the interval 2.837 and 6.275. So this tells us that we are 95% confident that the interval from about 2,837, right, to 6,275 of miles captures the true mean difference in measured in tire wear, right? So, yeah, this tells us that the difference between the methods, right, is the true mean difference would be between 2,837 and 6,275. So for part B, it asked us, does your interval in part A give convincing evidence of a difference in the two methods of estimating tire wear? Justify your answer. Well, surely it does, right? Because the average population mean, right? The average population mean is between 2,837 and 6,275. So since this interval is completely positive, we can clearly see that the method for the weight, right, gave bigger numbers than the method for the groove, right? So I just wrote that here. Since the entire interval is positive and we measured weight minus groove, we are reasonably sure that the measurement by the weight method is giving the larger numbers than the measurement by the groove method on average.